So a little introduction. I'm Duffie Cooley. I'm the field CTO at Isovalent. Isovalent is now part of Cisco. We're still doing all the same things we were doing before we were part of Cisco. Nothing's really changed for us. And we're continuing to go to market. So if you ever want to hear more about Cilium, eBPF, Tetragon, any of those things, definitely find the guy in the hat and ask him questions.
My name is Natalia. I'm the product lead for runtime security at Isovalent, which is now part of Cisco.
So this is our agenda. We're going to kind of introduce a few of the ideas, like talking about like what is Seccomp, get into some eBPF stuff, maybe do a little demonstration of some things, and then we're going to talk about kind of the advantages and disadvantages of each technology. So to get started, I wanted to introduce Seccomp. Seccomp is actually stands for Secure Computing. It was introduced in 2005, well before many of the other primitives of containers, right? We didn't really have a lot of the other things that make up a container today. And it was initially introduced to help limit applications that were running on a server in the old style without containers that share a kernel between each other, right? So like limiting that. And what are they actually limiting? They're limiting things like, you know, any application that opens a file might be, like I would need a system call that's called open at, or if you're opening a socket. But there are a bunch of other system calls in that API that perhaps you wouldn't want that application to be able to have, right? Like shutdown or reboot, or like, you know, some of the more obvious like system calls that you wouldn't really necessarily want applications that are sharing a Linux kernel to have that kind of control over the Linux kernel. It was also one of the first sandbox mechanisms, and from then we've seen so many more sandboxes, which is a term I absolutely love. Like anybody who's ever seen a sandbox, like why are they called sandboxes? But that idea of basically trying to contain or constrain an application within a specific scope of like what it's able to do against a shared resource has just come a long way. One of the examples is like the browser-based stuff, right? So like WebAssembly, a lot of these things kind of all sort of generated out of things like secure computing, right? Like that was the beginning, and we've continued to iterate, continued to improve, continued to like create more tools out there that create these sandboxes. Excuse me. So secure computing in practicality, like how it actually works, is when you start a process and you've defined a Seccomp profile, that Seccomp profile must be available before the process starts. And when that process starts, and based on that profile, it represents a one-way change into a secure mode where all of the system calls that application can make must be within the list that you provided. Now there's lots of ways to configure this. You can configure Seccomp to actually just warn you or tell you when the particular system call happens, but you can also constrain a given application to a set of system calls. And you can also do a combination of both of them. Any system call outside of that list, if you're in a more enforced mode, could result in either recording an event or in killing the process that tries to make that system call. One of the challenges of Seccomp, as I mentioned before, is that you kind of need to know ahead of time, like what that list of system calls, like what type of protections you're trying to apply before you start the process. And if you wanted to change that list, you have to like make a new profile with the changed list, stop the process, restart the process against the new set of profile. So it's a little, I mean, when you think about like when it was created and like what it was created for, this kind of makes sense, but now we're in this dynamic container age and things are a little bit different. As far as like how we use it inside of Kubernetes or in a cloud native way, there is actually an incredible project that's called the Security Profiles Operator. Definitely worth checking out if you're interested in Seccomp, AppArmor, or SE Linux. This, in my mind, is the state of the art for this, right? Because as I said, you have to kind of know, like you have to create a profile, you have to make that profile available on disk, and all of that has to line up before you can even start the application, because Seccomp, when you're using secure computing, you have to know that before you start the application up. And this means like before Docker run happens, all of those pieces have to be in place. And this tool makes that way, way easier. Not only does it make it easier to actually handle the distribution of security profiles, but it also makes it easier to do the discovery of them, to learn like what is normal for your application.
All right, so I will talk about like what is eBPF. So I think many of you know like what is eBPF at this point. There has been a lot of talks in this conference around it, so I will just do like a very quick high-level introduction. So eBPF allows you to extend the Linux kernel. And basically it allows you to write some C code or C program, load it into the kernel with some restrictions. Of course, it has to be safe. It cannot crash the kernel. It also cannot run forever, right? And then what the C code or C program allows you to do, it allows you to extract information, run some logic, or make decisions. And there are a lot of layers, and at almost everywhere we can actually hook into the kernel related to, for example, networking, like TCP/IP on the socket level, related to, for example, file access using file descriptors, or, for example, at the system call layer. And then this part will be actually important for this talk. And then I would like to call out like two really nice advantages here. So this can be done dynamically. So imagine this is very useful if you have like multiple clusters, multiple namespaces, multiple cloud providers. And then basically you can just like flip your BPF program on the fly. Imagine you want to block, for example, a new set of sensitive system calls, or you would like to block a new CVE. You could actually do this without even rebooting your node, rebooting your, for example, management pod, or even rebooting, for example, your application. So during this like upgrade, everything keeps running, and then the upgrade will be seamless. And then the other nice aspect that it's like minimally invasive. So since you don't need to wake up user space all the time, like it just takes away more or less CPU and memory. And then, so why is it interesting? Like, what are the answers that, or what are the questions that we can answer with eBPF? So you can ask questions like, okay, what binaries have run in the past or are running now in my system? And then this system can be, for example, Kubernetes nodes, Kubernetes workloads, external VMs, or what version of these like binaries or libraries are running now. Like, are there any, for example, vulnerable OpenSSL versions? Or what network connections have been made, for example, from my Kubernetes workload. Like, let's imagine you have like a Kubernetes pod running and for an hour, and then it just like start to reach out to a malicious S3 bucket. You kind of would like to know that. Or for example, were there any sensitive file accessed from that workload? And then, of course, like what system calls have been executed from my workload? Were there any sensitive system calls invoked? Were there any CV exploited, and so on. And then we would like to base this solution on Tetragon, which is basically like an eBPF-based runtime security observability and enforcement tool. And then it's actually just an agent, like it runs on the top of any Linux operating system. In case of Kubernetes, it's actually a daemon set. And then in case of like external VMs, it's a systemd managed binary. And then it uses eBPF to extract data from many layers. And then you can see it on the pictures. We have visibility into data access, file access. We have visibility into Linux namespaces, process capabilities, and then actually its changes. And then network connectivity, S3, L4 layer on the socket layer, or S7, TLS, HTTP, DNS. And then what's going to be important is actually the process execution and the system call activity.
Awesome. Yeah, so in my mind, the Tetragon piece is definitely state of the art for the other side of things, right? So like we talked about Seccomp profile operator being the state of the art for Seccomp. eBPF, absolutely Tetragon is the state of the art. So I wanted to give a huge shout out to Sasha Gunnert and the team that are actually working on this project, because it is a big undertaking. The SBO, does, like I said, does all of the hard work of generating and pushing security profiles to all of the nodes. And as I mentioned before, the profile must be present on the disk before the container can start. Now, this is actually, I thought this was pretty fascinating when I was doing this work, but what I learned when I was kind of looking at the security profile operator is that like, you can actually use it to say start a container on the pause container, which doesn't make any system calls itself, right? And if you do that, you can see all of the system calls that the given container runtime requires. Now this is interesting because it means that in Seccomp, right, you have to include the system calls that the container runtime requires, as well as any system calls that your application requires, right? So depending on if you're using crun or runc, like they're actually different sets. I mean, they differ. Crun uses 65 system calls just for the runtime, and runc uses 78. And some of those system calls seem kind of risky, right? Like some of those things like unshare or being able to change the permissions of a binary and make it available to anything. Or like there are some system calls in that set that could represent risk to allowing you to do container escapes and that sort of stuff. So that was kind of a surprise for me when I was actually digging into this, but yeah, it's super interesting that they use different sets of system calls. So one of the things I like about the eBPF and the Seccomp thing is that it's not one or the other. Like you're not required to just use one or the other. You could actually use them both together, right? So because of the list of system calls that you must include for the container runtime, if you said, well, okay, it's fine if the container runtime uses them, but I want to be notified when my application tries to use unshare, right? I want to be notified when my application does try to make these restricted or what I consider to be high-risk system calls. I have to allow them because I'm in a container runtime, but that doesn't mean I don't want to know when they happen, right? And that's where I feel like that's where the two of them together really represent an incredible capability.
All right, so I will talk about, like, for example, how eBPF and Tetragon could actually like restrict those system calls, like the known bad sensitive system calls. So how Tetragon implements like Kubernetes identity-aware syscall enforcement, where it implements it via custom resource definition. It's called sandbox policies, and then I will just talk about like how does it work, and then what the engineering team needed to implement in the BPF side to work correctly. So we have like 3 main components here, and then I will just start with the first, which is the policy definition itself. So as you can see on the left side or on the right side, these sandbox policies can be namespaced or cluster-wide with pod label selectors. And then it's important to call out that these are like very declarative. So you can actually specify like, okay, this is the namespace that I would like to apply this policy on, or this is the pod that I would like to apply the policy on. And then after that, you can just say like, hey, these are the known bad sensitive system calls that I would like to take some action on. And then after that, you can actually say like, hey, I would like to get an alert, like audit, or I actually want to block those system calls. And then 2 nice advantages here. One is that it's actually dynamic. So you can just like modify these policies on the fly. You can just do like kubectl apply, and then you could do that after the pod has started. And then the second advantage is here is that it's like very high level. So the BPF engineers can still innovate and then use newer BPF or kernel features. Meanwhile, the user doesn't even have to do anything. They just need to modify this policy. And then this can be like one example alert that you would get like during a sensitive system call invoke. So for example, you could see like, hey, on the sensitive namespace Kubernetes namespace, there was an nginx pod, and then well, it invoked the sysmount system call and tried to mount like devsd to the devsd file system from the node to the TMP directory. And then you could see like the capabilities, Linux namespaces, and then the process credentials. So the second part is like the Kubernetes identity-aware selectors. And then, so this can be like the namespace policies itself or the pod label filters. And then it's important to note that for observability, the in-kernel filtering is important for like performance reasons. So we can keep the CPU and the memory low, but you can live with the filtering, or at least some of the filtering living in user space. But for enforcement, it's important to note that user space filtering is not an option. Like the filtering has to happen in kernel in line with the operation. And then what that means, like those Kubernetes identity-aware selectors, like both on the workload side, needs to map to the BPF code. So how we implemented it? Well, we actually mapped the Kubernetes workloads to C groups. So C groups are a Linux mechanism to actually manage and isolate containers. So for example, container runtimes, container CRI/O, they create their own C group like hierarchy. This is just like a very simple example. you can see systemd on the top, and then you can see the Kubernetes pods under kube pods, and then usually you have like one C group per Kubernetes pod, and then basically one C group per container. So what we do on the Tetragon side, it's actually pretty simple. We create a BPF map, and then basically on that map, we assign a unique ID to each policy. And that maps to another map, where we keep actually the C group IDs for the containers to which this policy applies. So whenever you actually apply a new policy, you say like, hey, kubectl apply. Well, Tetragon actually updates or initializes the map. So it looks up actually that like 3-group hierarchy under the 3-group file system, checks like which Kubernetes workloads matches to which C group, and then whether the policy actually applies to it, and then puts it into the map. And then after that, well, Tetragon loads the BPF programs into the kernel, and at this point, you have the BPF program loaded, and then basically they check if the policy applies to that certain process. And then whenever there is like new pods coming, or there are like pod label updates, well, the Tetragon agent gets a notification from the API server, and then it just like keeps updating the map. And then the last piece is, we call it like reduced time window, or for example, like an advanced configuration. So it can happen that you, for example, kubectl apply a pod, the Kubernetes API server reaches out to kubelet reaches out to the container runtime, and then it starts the container. But it can still happen that this container starts with a policy applied to it, but without the policy actually being loaded. It's because the Tetragon agent didn't get the notification from the Kubernetes API server yet, so it didn't actually have time to set up the BPF programs. So as an advanced configuration, what we did, we actually like implemented a daemon set, and then what it does is just hooks into the underlying container runtime by configuring runtime hooks, and then say, whenever there is like a new container starting, then please execute this binary from the daemon set. And then what it does, it actually just reaches out to the Tetragon agent. The Tetragon agent basically updates this map, and then say it goes back to the daemon set, and then it goes back to the container runtime and say like, hey, the policy filter BPF map is set up, the policy is actually configured, and then you can actually start that container. And then one minor details, if the Tetragon agent is done, then basically we say, okay, we cannot actually guarantee that the policy is set up, and then it will be applied, so please don't start the container. And then of course, it's actually like configurable, so you can say like, okay, this namespace is actually trusted, and then, for example, these workloads are trusted, and then those namespaces or those pods can start. So for example, this can be kube system, so the main services and Tetragon agent are actually able to start. And then after that, I will just like play a quick demo video, which would actually like block sensitive system calls or like bad known system calls or on a sensitive Kubernetes namespace. So what I did here is like we used an AWS cluster, 10 nodes. They are running Amazon Linux. Tetragon is running on each node as a daemon set. You will see the Tetragon runtime hooks also as a daemon set. And then I configured a sensitive namespace, Kubernetes namespace, and then there will be like an Nginx pod running on it. And then what I will do, I will apply a sensitive syscalls Tetragon sandbox policy. And then what I will do after that, I will just like kubectl exec into the Nginx pod, try to execute some commands, and then which would invoke sensitive system calls, and then you would see that all of those will be blocked. So I will just play the video. So here I'm already connected to the Kubernetes cluster, and then we can actually see that on the sensitive namespace, Kubernetes namespace, there is an Nginx pod up and running. And then in the middle, I will actually show the Tetragon sandbox policy, which I will apply to this sensitive namespace, Kubernetes namespace. And then this is going to be the CMO. And then what it does is actually pretty simple. It enforces a set of like known bad system calls. For example, syssage root, sysclock set time, syspivot root, sysmount, sysmadvise, sysunshare, syssetns, and so on. And then in additionally blocking these system calls, we will get like one event when the system calls are going to be invoked. So I will just apply this sensitive syscalls Tetragon sandbox policy on this specific Kubernetes namespace. We can actually see that it was created, and then I will just double check if the policy got installed very quickly. And then we can see that it was installed 11 seconds ago and then up and running. And then as a next step on the bottom terminal, I'm actually inside the Tetragon container on the same node where the Nginx pod is running. So I can actually start to observe these like security audit or enforcement JSON events, which will be coming from the Nginx pod. So I will just start to do that. And then as a last step, I will just keep petal exec into the Nginx pod on the top. And then I will execute some commands which would invoke those sensitive system calls. So we can actually see that on the bottom that the beam-bash binary was executed from the Nginx pod. This is one runtime execution event. And then as a first command, I will just try to run sage root. And then we can see that the operation was not permitted, which means that the syscall enforcement policy was actually working. And then if we go to the bottom, we can actually see the alert as well. So we can see that on the sensitive namespace from the Nginx pod, there was a user as being sage root binary, which tried to actually invoke the syssage root sensitive system call. And then we can actually see that it was enforced. So as a next step, I will try to execute, for example, mount, and then mount the dev sde1 file system from the node to the tmp directory on the pod. And then we can actually see that it was not successful as well. We got permission denied error. And then in the events, we can actually see that the sysmount system call was enforced from the user SB mount binary on the Nginx pod. And then as a last step, I can just try to execute, for example, pivot root. And then we will see that the operation failed as well. And then in the alerts, we can actually see the enforcement event the same way as we saw before from the Nginx pod on the sensitive namespace. The syspivot root system call was not successful from the user as being pivot root binary. All right, and then as a last step, we will just do a quick comparison between the two, because both of those technologies has like advantages and then disadvantages. So as Duffie mentioned, so on the eBPF side, advantages can be like it's dynamic, right? So the Kubernetes application doesn't need to be restarted for the policy to take effect, or the underlying Kubernetes node doesn't need to be rebooted. It can be also very flexible. So you mentioned like Kubernetes identity-aware metadata, like pod labels, namespaces, but you could do like binaries, hashes, or you could actually filter on like process capabilities, Linux namespaces, Unix credentials. Well, disadvantages can be like, since we are using eBPF, the BTF metadata file needs to be present on the node. And then, of course, like newer kernel would be needed, for example, for advanced features. So, for example, if you want to like multi-kpop support, you might need like a 6.1 kernel to be able to load the policy faster. But on the Seccomp side,
So on the Seccomp side, one of the advantages is that there isn't a window of time between the process starting and the process being protected. However, and there's also really good tooling, like the security operator tooling that I was talking about before, gives you the ability to actually discover what system calls your application is making at runtime. You can create like basically a profile recording and then learn from that profile recording what that list of system calls needs to be able to allow your application. And you can actually record that for as long as it takes for you to feel comfortable with the fact that you've made all of the system calls you're going to make, right? So really good tooling out there. Some of the disadvantages are it's hard to iterate, right? If you're going to make a change, if you need to make a change to that policy, that means restarting the application. And that's not something that a lot of people like to do in production. You also, and as I mentioned before, you also have to allow for all of the system calls required by the container runtime, not just those for your application, which is a surprise. And that's where, again, I feel like the combination of these two really shines, because you can actually you can allow for the container runtime and then further limit. One of the other pieces to this is Seccomp, again, because it was built in a time when there were just applications on servers. It wasn't a container time. It means that when you get events, if you're trying to do learning, that profile learning stuff, you're not going to get all of the metadata that like Tetragon gives you, right? Tetragon, for each of those events, actually says it was this pod, it was this node, it was this time, etc. Seccomp is like, it was this PID that tried to make this system call, and you're like, I'll figure that out. Yeah.
All right, so yeah, thank you everyone for coming, and I will open up for Q&A. If you're interested in Tetragon, please go to the Cilium Tetragon repository or join the OSS Slack channel. And actually, the engineer who implemented the Kubernetes identity-aware selectors are sitting over there. So if you have questions, then you can also ask. Thank you.
Thank you so much for being here. If you have questions, there's 2 microphones right in the middle. You first.
Hello. So is there any plans to add like host-based policies for Tetragon so that you could define like for this node group, you can have these rules on the host itself, so kubelet can and cannot do certain things, for example?
Yeah, I mean, so you could actually specify like the host PID, right? So you could actually match on like host level processes as well.
Oh, perfect. Thank you.
For the Seccomp profiles, are they host-wide or are they per container to be defined?
Yeah, so the Seccomp profiles can actually be per container, per process, really, right? So if you had multiple containers in a pod, you can define a profile for each of the containers, but it is per process the way you should think about it.
Do I still need SE Linux or AppArmor if I use Tetragon?
So they do different things, right? Seccomp is more about protecting the kernel. AppArmor and SE Linux are more, they go a lot farther into protecting a lot of the other shared resources on the host, right? Like the file system access, like whether, like if you look into SE Linux and the container orchestration side of things, it actually cares that the UID of the process running and its permissions as it relates to any file system access that might be on the underlying host. So even mounting a volume in with SE Linux, you have to be very specific about making sure you have the right permissions to actually even allow for that. So they do different things. I do think that it's a belt and suspenders approach. I don't think it's just one or the other. However, like what's really interesting, I guess to your point, is like when you look at the eBPF capabilities, it is actually much more wide-ranging, right? So like if you get into like enforcing these things with Tetragon, you can actually care more about the file system. You can care more about lots more of these things than just Seccomp. And I think that's pretty interesting.
For Tetragon, if I have a cluster with many nodes, let's say 20 nodes, how does the policies get updated dynamically? How easy is that? Do I have to touch each node to get a policy update, or there's a system behind that?
I'm having a hard time with you. Can you get a little closer to the microphone?
Oh, sorry.
No, I think I understood the question.
Oh,
Okay.
So basically, we have like the Tetragon agent, and then we have like an operator, and then the operator actually takes care of the CRD management. So when you say like kubectl apply, like it will get automatically updated on each node, depending where the operator is.
So it's a synchronous update,
Yeah.
immediate update.
Yeah.
Thank you.
You mentioned that to do the blocking, you have to do the filtering in the kernel.
Yeah.
Is that a global parameter so that if I want to do blocking, I have to do all my processing of stuff in the kernel, or is stuff still able to go out for external processing as well?
It's in the kernel, but if you're interested in the BPF detailed implementation, I think John and Cornelius can chime in here.
It is interesting. I think maybe, oh, sorry. I think maybe part of your question is like, if I write an eBPF program, can I have that filter on like everything that's happening against that pattern that I'm watching for, as opposed to, can I hook this to specific applications and watch for those applications to do things I don't expect? Is that where you're going?
Yeah, granularity there, so that you can have the best of both worlds, where you can still send stuff out for external processing, but then block if you need to inside.
Yeah, in that scenario, you can do a little bit of both, right? Like, you can actually watch for like any system calls we made, and you can correlate them based on the events that we're catching for like what's actually watching. But when it comes to enforcement, like you are trying to key that enforcement on specific applications that you're matching, right? But if you just want to be inundated with like what is everything doing, we can definitely show you that. Yeah. All right. Well, thank you again.
Thank you so much.